Hi, good morning to everybody again. And the first speaker of the morning is Professor COUGHLAN. He will give a talk on computer vision-based assistive technology for the visually impaired. He's coming from the Smith Kettlewell Eye Research Institute. Okay. Please.
Okay. Thank you very much. How's the sound? Okay, good. Thank you very much for inviting me. I do want people to know I am actually a quarter Italian, but I'm from that part of the ancestry is northern Italy. So I want to follow up a little bit on the basic issue of computer vision is a very powerful tool for assistive technology, but what are the commonly used assistive technologies that are already out there, just to orient ourselves. And the main point I want to make here is that most of what's out there that's actually in use is extremely simple and extremely reliable. So we have the white cane, lenses, screen magnifiers, accessible pedestrian signals at crosswalks, the things that make sound when the walk light is illuminated, detectable warning surfaces, such as bumps on curb ramps. Extremely sort of low tech in some sense. And perhaps higher tech, but from a computer vision standpoint, extremely reliable. Some of the features you have on smartphones nowadays, text-to-speech, essential and quite reliable. GPS applications, which are very useful for outdoor navigation and transit, et cetera. Not without their glitches, but again, GPS is a standard, and it works quite well in a lot of settings. And obviously, and this is relating to some of the things that Seth already said in his talk, there are a lot more kinds of assistance that are needed by blind and visually impaired people. Wayfinding, getting from one point to another. Assistance, wayfinding is needed indoors and outdoors. And of course, one technical issue is that GPS is unavailable indoors. Orientation and mobility requires both self-localization at a high resolution. To avoid that pothole or something, you need, probably a few inches resolution accuracy, and environmental sensing. So where do you walk exactly if you want to board a bus? How do you avoid the obstacles on the way? The need to read all sorts of text in the environment, printed text and signs, for instance. A lot of devices and appliances, as Seth mentioned, are actually requiring you to be able to access visual displays, LEDs and LCDs. And even if you have low vision, some vision, very often these displays are low contrast and difficult to see. And so a lot of people at my institute who visit come by and say, oh, you're doing computer vision for the blind. What could be more obvious? Isn't everyone doing that? It's kind of a funny question. And it does sound very promising, and it is very promising, to combine computer vision with the needs of blind and visually impaired people. But the two basic answers I like to give to people who ask this question, and I wanted to make this point at this particular workshop, it's very difficult to make assistive technology that is actually useful and reliable and convenient. It's a very high bar. And it's also, it's even harder to make computer vision work reliably under the sorts of unconstrained conditions that you need in the field. Okay, and just to outline a few sort of successes and limitations of computer vision, just a few case studies. One is optical character recognition, and again, Seth talked a little bit about this as well. It's been developed for decades. It's quite reliable in certain contexts. But basically, OCR is really only quite reliable under good conditions, when you have standard fonts, a uniform background, some sort of image that's very high quality with high resolution and high contrast, with a minimum of clutter in the image, the type of images you get from a flatbed scanner with a document on it, for instance. And when conditions are less than ideal, OCR tends to falter. And so here's an example of an image taken from a smartphone camera of a sign in a corridor. It says mechanical. The image on the left is a crisp image. The image on the right is an image that is readable to most people with normal vision. It's the same sign, but there's motion blur. And one of the practical sort of difficulties you often encounter with computer vision is the limitations of the cameras, and particularly in indoor settings when the lighting is not so bright compared to outdoors. And so if you feed in this slightly blurred image of the word mechanical to an OCR engine, you get something a little bit wrong. It gets a few letters wrong in the interpretation. A second case study, stereo depth reconstruction. And the idea of stereo is to infer depth in a scene by using two slightly different views of the scene. Here we have a left and right view of a colorful scene, and on the right is the disparity, which is basically something like the depth map. And the lighter pixels mean that the object is closer to the camera. So it's really a quite powerful technique. There are many complications. If you have challenging lighting conditions, you're likely to encounter a number of underexposed or overexposed pixels, especially when you're outdoors and especially when it's sunny. Here's a picture of a car taken by a stereo camera, and you can see that the shadow region under the car is quite dark, and actually the depth is resolved somewhat successfully in that area. There are other portions of the scene where the light is just too bright and stereo needs some sort of texture, and absent texture it gets confused. Now, of course, there are lots of alternatives to sort of passive stereo and things like LiDAR and time-of-flight sensors and so forth. But it's really hard to, it's dangerous to assume that these techniques are going to be reliable in a lot of natural conditions. A third sort of maybe success story of computer vision, if you want to call it that, is object detection or recognition, which can work very well under constrained conditions. So for instance, if someone wants to do face recognition on maybe photos in Facebook or something, if the photos are well composed, if you have a pretty good idea of who the possible identities of the people are, then it's often quite practical to identify the faces reliably. But when you have more complicated images, uncomposed, you know, a scene in an airport or maybe at a party or something, face recognition is really very, very difficult. And also just the general problem of objects that are not rigid, things that are deformable or have moving parts, people or animals, for instance. Some modern algorithms have still some pretty spectacular failures. The failures are shown here on the right column. So the theme about computer vision is that the state of the art is always improving. And while the algorithms are improving, the hardware to support it is also improving at the same time. It's all getting better and better. But still, most algorithms are quite brittle, requiring certain assumptions to be met. And very often the algorithms are trained on well-behaved and well-composed images. And when you don't have them well composed, when you have difficult lighting, that poses a lot of challenges. And so I want to just talk about, and also just the other aspect of computer vision to keep in mind. Typically, you're going to have more success with narrowly defined tasks. For instance, detecting and reading a barcode in an image, much easier than saying something like find your friend in the airport. And high-level tasks that are not even necessarily expressly visual. Is there a place for me to sit down? How do I get to the conference room? Those are almost impossible problems to solve just using computer vision at this time. And you have to also consider the consequences of failure. If an algorithm makes mistakes in recognizing a face, that's one thing. If it's driving the car for you and makes a mistake, that's another thing. So, you know, the main point I want to bring out in this talk is that computer vision is just one of a whole suite of technologies that complement each other. And I'm just going to talk briefly about a few technologies that sort of work well to augment computer vision. And the first is sensor technologies. Sensors are becoming ubiquitous, in part because of the development of smartphones. And your typical smartphone has an accelerometer, which is a tilt sensor basically, a compass built in, GPS, a gyroscope. I think some of the newer ones have humidity sensors, barometers, all these different things. And it's really quite exciting that these sensors are available in these compact smartphones. And so just to give you an example of some of the kinds of things you can do with sensors, I'm just going to draw briefly on an example of my work. There's a project I'm working on called CrossWatch, which is a smartphone-based system which is designed to give information and guidance to blind travelers at traffic intersections. So you're standing at a traffic intersection and you want to know, where am I? How do I align myself to the crosswalk? You might want to know when the walk light is illuminated, those kinds of questions. And one of the challenges in trying to apply something like computer vision to this problem is, well, how could a blind user aim a camera properly? And again, these are issues that Seth has already raised in his talk. To take good images requires aiming. And so for this particular application, one solution that we've come up with is rather than, in older work, we did sort of ask subjects to try to just aim the camera precisely towards the crosswalk, and it's extremely challenging. And our approach now is to have the person take an entire panorama of the intersection. And that panorama could be 360 degrees, it could be 180 degrees, something like that. And still the challenge remains, okay, maybe you don't have to localize perfectly left to right, but you don't want to be pointing too far up or down. And this is a very simple example of where the accelerometer is very useful, because the accelerometer can ensure that the person holds the camera horizontally. So as you pan in a circle, anytime the orientation of the camera deviates too much from horizontal, the smartphone issues a vibration warning. And so with this a little bit of training, you can get a blind person to acquire a very usable panorama, such as this example. And just to follow up the kinds of things that CrossWatch would then do with this imagery, we can then create an aerial view. What would the bird's eye view of the intersection be, which is basically undoing the perspective projection. And once you have an aerial view, you can use the magnetometer, the built-in compass, to estimate the rough direction of north. And then you can assign some sort of orientation to this map of the intersection. And since you're using a smartphone that has GPS, the GPS actually tells you what intersection you're at. And you can then have the software look up a template. So a template that says, oh, at this intersection, we happen to know what the layout of the intersection is. And you can basically match this aerial view of the image with a template to estimate where you're standing with much better precision than GPS. You might want to localize yourself and to align yourself to the crosswalk. And GPS might give you 10 meters, which is not very good. We're aiming for more like a meter or something, so that you really can center yourself in the crosswalk. Okay, so that's just an example of the kinds of ways that sensors can really enhance computer vision. And another technology I'm just going to talk about very briefly, Jeff Bigham is going to be giving a talk today. I'm sure he'll go into far more detail on this. Crowdsourcing and humans in the loop. So the obvious question nowadays is, why do we have to rely on computer vision solely to analyze or interpret images? Every smartphone has an internet connection. You could actually send images to a central server and have sighted participants interpret images for you. And not only is a sighted person perhaps more reliable and accurate than a computer vision algorithm, but that person can also answer very open-ended, high-level questions that really address the exact need that the user has. So for instance, here's a picture. From this picture, you might wonder, well, where am I? A computer vision algorithm might have a really tough time of figuring out anything other than the presence of pedestrians. But most sighted people would say, oh, you're outside of a bank, there's an ATM, and there seems to be kind of a long line for the ATM. The question I mentioned before, is there a place to sit down, perhaps from a panorama image or something? A sighted person could perhaps tell you where the chairs are. And notice that some chairs are taken, but there are empty benches elsewhere, that kind of thing. And just very quickly, to mention that computer vision and crowdsourcing are very complementary sorts of technologies. Computer vision excels at solving constrained tasks. Very often you can do these tasks quickly, in real time. And if it's important for the application, you can do it on board the smartphone, not necessarily have to beam it to a server. And that can be an important thing if you have limited connectivity, limited bandwidth. or if you're trying to analyze video, that can be quite challenging to do quickly. Crowdsourcing excels at much less constrained problems. They can reduce the load on your smartphone, which actually could reduce the drain on the battery, for instance. But of course, there are a lot of issues to think about with entailing the quality of the operators of who are available and how many are available when you need them. So that's all I'm going to say about crowdsourcing for the moment. So computer vision can be augmented very nicely with complementary technologies such as sensors and crowdsourcing. And so really, two main challenges sort of remain if you want to create an assistive technology that relies on some sort of image analysis. And the first is acquiring good images, and the second is communicating spatial information about the environment to the user. So how do you aim a camera when you have very little vision? It's really important to have good feedback, preferably in real time. There's a whole bunch of sort of new work on this issue. For instance, there's work on finding salient portions of a scene and helping a blind person take photographs by alerting them to where the salient things are in the scene. My collaborator, R.MANDUCHI, is going to talk about our work in his talk this afternoon, addressing sort of this aiming issue very specifically in the context of a certain visual target as well. And you just mentioned that there are a lot of practical considerations that compound the problem of knowing where to aim the camera. The first thing is the resolution. If you're too far away for the detection system to resolve the target of interest, you're out of luck. Field of view, especially when you get closer to a target, it actually paradoxically gets easier, as Roberto will explain, it gets easier to lose lock. It becomes easier to lose sight of the target in the field of view of the camera. And compared to the human visual system, most cameras that you have on smartphones have very narrow fields of view. The speed of the system, if the feedback is very slow, that's going to really hamper the user who's trying to explore a scene. And of course, challenging lighting conditions. And just a point, sort of a preview of some things that Roberto is going to talk about, some of these considerations can be traded off one for the other. You might actually artificially reduce the camera resolution and thereby speed up the feedback process. And there are pros and cons to that. And one thing I want to talk about briefly as well is there really needs to be, we need to think a lot in this sort of field about different form factors. You know, the smartphone was this new toy, 5 years ago or so, that really opened up a lot of possibilities. And it's still sort of the easiest thing to sort of sell the idea of. If you can tell someone all they have to do is take out their smartphone, that's already sort of a plus for whatever approach you're suggesting, you're proposing. But there are a lot of other things that are going to interface to your smartphone that we have to think about, and particularly form factors for different cameras. And here's a picture, for instance, of Google Glass. And all these different form factors have different properties for how you hold the camera, if you have to hold it at all, how you aim the camera, the field of view, that kind of thing. And also wearable cameras as well. Omnidirectional, we're so caught up in knowing how to aim the camera in the right direction. Well, certainly you can think about omnidirectional cameras as well, and there are a whole host of trade-offs to consider. But these have to be considered. And this issue of the form factor also relates to proprioception, how you know sort of where you are in space and what you're pointing to, for instance. So you may have system feedback from your computer vision system that's telling you about a direction in space. But there is a bit of a confound between what the system thinks is a direction. So the system is always using something like the camera line of sight as a reference direction. How do you relate that to the body direction? So if you're a blind person and you're holding a smartphone app that's supposed to beep when it finds something, if you ask a blind person using this application, can you walk to the target, which is indicated by the beeping, proprioception varies quite a bit among different people. And for some people, some people may hold a smartphone straight and advance their torso in the right direction. For other people, they may not be aware of a huge sort of divergence between the direction that they're about to walk in and the direction they're holding the smartphone. So it's a very sort of variable thing. It's a very important thing to think about. And it also brings up the issues with different sorts of camera form factors. So I think a really important question over the next few years is going to be understanding these issues, what is the easiest for a for a particular person or task? Is it easiest to point a camera that's maybe attached to your head, or is it easier to point a camera mounted on your chest, or a smartphone? And I think that there needs to be a lot more sort of research into these different pointing sort of approaches. And I think it's going to depend, the answer is going to depend a lot on the details of the tasks, of course. And then the final point is communicating spatial information to users, and this also came up in Seth's talk. Even if your system has acquired good images and is making really good inferences about the world out there, it still has to communicate effectively to the user. And again, how to communicate effectively, it's a huge challenge. It also depends an enormous amount on the task. So for wayfinding, maybe step-by-step verbal directions are best. You're walking down a sidewalk, and you tell the person, turn left at the corner, because you can exploit a number of natural reference points, such as maybe the corner. But verbal directions are not always so good for other tasks. So for instance, here's an image of a very schematic image, an aerial view of a crosswalk, a two-stripe crosswalk, and a person holding a smartphone. And in situation one, the person is pointing the smartphone and their torso parallel to the crosswalk, but they are displaced relative to the crosswalk. In situation two, the person is actually centered in the crosswalk, but if they were to start walking, they would soon be veering out of the crosswalk. They have the improper rotation. So conveying the difference between you need to translate a meter or so to the right versus you need to rotate left, 30 degrees, that can be a very challenging user interface thing to do. And I'm not going to go into solutions in much detail, just to say that there are a lot of ingredients to consider. One thing is spatialized sound. So, of course, Seth mentioned these tactile displays, which I think are very promising as well. Spatialized sound is the idea of using stereo sound to convey three-dimensional directions. And for certain users, that may be a very effective interface, provided you have good stereo hearing, binaural hearing. And then gesture recognition. Some of the projects that Seth has been involved in, like Fifth Sense, relate to this. And also there's a project called OrCam for low vision users, where, for instance, you can indicate direction to the system, and there's a potential for interacting with the system by just using your finger to point. And so the system could not only listen or sort of watch to where you're pointing, but also could direct you and say, okay, move your finger to the right until we say you're in the right direction. And that could tell the person sort of where they need to go. So there's so much more to think about than just making a smartphone app beep at you to give you information. Okay, so just quickly, the conclusions. Computer vision is just one of several technologies. It's sort of a whole ecosystem of technologies that can work together to solve problems for visually impaired persons. And it's really essential to design a system that has an appropriate user interface and appropriate hardware, different form factors and so forth, that facilitates acquiring usable images and communicating the information effectively with users. Okay, and just a final note, kind of a caveat, you won't really know for sure whether a system is solving a real problem that blind people care about, whether it's effective, whether it's easy to use, until you test it with actual end users. And I've seen a lot of projects where people didn't do the testing at all or waited until the very end of the project. I've done that myself as well. And it's really important, especially if people, maybe not so much in this room, but if people are just getting into this research, it's essential to involve blind and low vision people as early as possible. So thank you very much.
We are running late, but if there is one question, while maybe the next speaker is setting up his computer. Okay, if there are no questions, thank you. And
thank you.
Please. The next speaker
nice to see you.
Is Marcello Pelillo from the University of Venice, Università di Venezia. And the title of his talk is Social Sense Making for the Visually Impaired. And I'm asking to all the speakers to be strict on the time because we are already late.
Okay, thanks Laura for your presentation. First of all, let me thank the organizers of this workshop for inviting me today. I'm really honored to be here. Today I'll be talking about an ongoing Italian project which just started, which I'm coordinating, basically which aims at developing a system for improving the social inclusion of visually impaired people, based on computer vision technologies. Let me start by just mentioning the people who are involved in this project, who, as I said before, just started. So here, actually, in this talk, I'm not going to talk about what we have done, but what we plan to do in the coming year, in the coming months, actually. So here is the consortium. Actually, the consortium involves all the top Italian researchers in computer vision, machine learning, and multimedia technologies and control theory. And actually, it's nice to notice also that all the people involved are located in some of the most beautiful cities in Italy. So this is kind of nice when we run our meetings, you know. By the way, so I'm not sure. Okay. So here is the state of the art. I don't think I have to dwell more on this because both Seth talked and James talked about the state of the art in terms of computer vision-based assistive technology. Quite recently, actually, James and Roberto published a paper in Communications of the ACM just last year, and he kind of grouped the state-of-the-art activity into 4 groups. So as Seth said in his talk, we have system which actually help the user to detect obstacles, to detect stairs, and so on and so forth. There are systems which allows the user to navigate, to move from one place to another one. There are systems which allows the visually impaired people to read text. And more recently, there are systems which are able to, to recognize objects, for example. And so one observation, and this actually was one of the conclusions of this paper, is that the majority of the systems around basically deal with the physical surrounding. They are not really interested in the social context, but see the Fifth Sense project, as we just learned a few minutes ago, because they started working on the social interaction domain. And actually what we want to do in our project is kind of a complementary of that project. We start when they stop, and I'm going to show this later. So the project objectives are, we want to develop some technological tool which will enable visually impaired people to improve their social sense-making, to deal more effectively with social relationships and environments. And of course, our philosophy will be to design and implement systems which are low cost, and we are as non-obtrusive as possible, and of course, as friendly as possible, in order not to create psychological barriers which would hamper its use. So we have just seen that computer vision might be, difficult. Solving computer vision problems are quite difficult in many situations. We're going to restrict our attention to a very favorable scenario. Actually, we're going to consider only indoor environments. And this will actually allow us not to deal with problems like lighting condition and so on and so forth, which might make a difference in the system. We are going to consider 2 scenarios, actually, a short-range conversational one, so mainly static. So we are envisaging a situation like, a lecture hall or an office, a meeting room, and stuff like that, a corridor, and so on and so forth. So we are considering a short-range scenario, mainly conversational situations, such as a meeting, an interview, where basically there is a face-to-face interaction. And we are also considering a medium-range situation, like, for example, walking down a corridor, going out from a room, exiting from the building, and so on and so forth. In order to address these issues, we're going to consider a variety of sensors and devices. To deal with the medium range situations, we're going to use ambient cameras in order to provide the system a global view of the situation. And then we are using both wearable cameras or glass cameras, for example, and smartphone cameras to get the first one actually will be used to focus on individuals or locations according to the user's focus of attention, while the smartphone cameras will be used basically to focus on people in different areas. Then we have also input devices like output devices, sorry, like earphones and non-invasive audio devices. We're going to minimize this because, as we listened before, it's not a good idea to have a lot of audios for the visually impaired. And also we're going to use tactile braille interfaces. All these devices will be communicated with a server over a wireless network. The idea is that mobile devices will be used to compute very simple computations like feature extraction and simple stuff, and while more complex computations will be done on the server. So a few years ago in a workshop which was organized by James Kettlewell and Roberto Manducchi in CVAVI 2008, a group from Arizona State University asked a few questions to a group of people, many of whom were actually visually impaired, and they conducted an anonymous survey in order to understand what are the functionalities that would be most desirable in a social setting. So they asked the following questions. These are 8 questions, and this is the mean score that they got, with the idea that 1 means strongly disagree and 5 means strongly agree. So you see what kind of things will be useful to do. For example, visually impaired people would like to know what facial expressions others are displaying while they are interacting with them. So I'm talking to another person. I would like to know whether he is understand what I'm saying, is disgusted or whatever, or is focusing his attention somewhere else, and so on and so forth. I don't know, question number 3, where I'm standing in a group of people, I would like to know the names of the people around me. And so we've seen that Fifth Sense project actually tried to address this question, trying to label the faces with a name. Or I would like to know what gestures or other body motions people are using when I am interacting with them, and so on and so forth. So we took this question seriously. So what we plan to do is to try and devise a system which tries to solve some of these questions, to answer some of these questions. So as far as of course, to do this stuff, we have, first of all, as we have seen before, to have a very robust phase detector system, for example, and we have a lot of the state of the art nowadays is very good. Here is a video which shows how robust are nowadays technique for tracking phases. This is a video taken from a group at Imperial College, which shows 3 state-of-the-art techniques for tracking phases. Here is an active appearance model. You see how robust it is. And the last one uses kernel methods. So of course, to access to the facial expression, first of all, we need to find phases and to track them over time. And another issue, as was pointed out by Seth before, was to name the people in my field of view. So here there are a few videos which are based on a paper published a few years ago, 2009. Actually, there's a sad note here because one of the authors of this paper suddenly passed away a few weeks ago. So this is really sad. By the way, you see this is a movie, and the system uses the screenplay to know the names of the characters, and you see in real time the system is able to give the right name to all the characters in this video. So the technology here is quite advanced. But this is stuff that is also being done in the Fifth Sense project. But so what we want to do in this project is to go beyond face recognition and beyond face detection and try to interpret nonverbal cues. And this is the novelty of this project. Actually, a very well-known study shows that as much as, from the psychological field, shows that as much as 65% of a two-person conversation relies on nonverbal cues, right? And you see how powerful our visual system and our brain is. For example, here, we just see the silhouette of these two persons, and it's just a black spot over a white background, and we are able to know a lot of things about here. First of all, there is a female, there is a male, but you can see that these guys are arguing very aggressively, and you can notice this using a lot of nonverbal cues like height, mutual gaze, posture, and so on and so forth. So nowadays in computer vision there is a whole new area which is called social signal processing. Actually, interestingly enough, this area was created more or less here at MIT a few years ago. Alex Pentel and his group invented this area and the name also. So the idea of recognizing the emotions of one person by using, facial expression, gesture, and so on and so forth is quite old, actually. Charles Darwin is usually credited to be one of the first that tried to, understand what are the emotions behind one's face. He also recognized quite rightly that this is quite difficult problem to solve because, as he says, the study of expression is difficult owing to the movements being often extremely slight and of a fleeting nature. And you see these are a few pictures taken from his book, which was published in 1872. You see several expressions from hatred here to joy, happiness, neutral phases, wrinkles on the forehead. You see here there are a few smiles. This is a neutral phase. This is a genuine smile, and this is a posed smile. Sometimes this is called Duchenne smile. Okay, so what we want to do now is that in the past century or so, we have went far beyond this idea. You will find in Darwin's book a lot of qualitative description of how you can recognize an expression of an emotion by looking at the face or a gesture. But nowadays, the situation is much more sophisticated. A few years ago, in the 70s, a group of psychologists led by Ekman introduced this facial action coding system. So basically, each muscle in the face has been minutely coded, and using this, a lot of action units, which are basically elementary expressional units, were introduced. I think there are some 46 or something like that. So for example, here you see A1, A2, A4 deal with the eyebrow. I don't know, A26 deals with the lips, with the mouth, and so on and so forth. So the idea they introduced was that we can analyze facial expression quantitatively using these action units, which actually tell us the contraction or the relaxation of the muscles, and we can try to understand what is the emotion behind this. So you can see here is happiness, and these are the action units which are involved. And here there are the action units which are involved in the 6 basic expression emotions: disgust, happiness, sadness, anger, fear, and surprise. And you see these are the action units involved in all these expressions. So the idea is that we can recognize these action units over time and try to classify, actually it's a classification problem, the corresponding emotion. Actually, tracking action units can be done online and in real time. This is again a video taken from a group in Imperial College. You see how the action units are tracked during the video, basically in real time. And using this and other information, one of the partners of this project, actually Niku Sebe, from the University of Trento, has developed a very powerful system for tracking the emotions over time. The goal, the purpose here was totally different. The idea was to analyze the facial expression when the viewer is watching the commercial. And this might have a lot of implications, And you see how the system works. It attaches a mesh points over the face, and you see how the 6 basic emotions are tracked over time. This commercial, this guy is watching actually ends with a funny story. So at the end of the video, we'll see a lot of happiness here. because he's smiling a lot. So this is done again in real time with a webcam, so low cost and real time things. Okay. But I know there are more than just the facial expression. We have to go beyond faces. This was clear already when Darwin published this work. I got this quote from his book, which is quite interesting. This is the typical expression that we all do when we want to say, what can I do, right? We do more or less this. Interestingly, he noticed that this happens in an intercultural way, something which goes beyond cultures. And so he says, when a man wishes to show that he cannot do something or prevent something being done, he often raises with a quick movement both shoulders. At the same time, if the whole gesture is complete, he bends his elbow closely inwards, raises his open hands, turning them all outwards, and so on and so forth. So he explained minutely what are the gestures involved in this what can I do movement. And here are a few examples taken by an actor. You see. This is an actor, though. Maybe he's implementing his ideas. By the way, so we have to go beyond phases in order to do that. And for example, in this what can I do expression, we have to monitor the shoulders because shoulders are shrugged. And so this is an example of how we can monitor the vertical displacement of the shoulder, while this is another system built in Alberto Del Bimbo's group at the University of Florence in our group. We're tracking the ends. This is using Kinect, though, but it can be done more or less in the same way using other technologies. So the fact that we are working indoor, of course, solves a lot of problems. We are thinking of other functionalities also. This is just a few things we want to do. For example, estimating visual attention using either gaze direction, which might be kind of difficult, or head pose. Localization and tracking of objects and people. This is something that the Fifth Sense project already does, but might be useful to integrate this module in our system. Identity discovery and identification, possibly upon request. Behavior understanding of individual and groups, and detection of anomalous situation. One of the things we want to do is to make transversal use of the machine learning techniques, because these are quite powerful. Let me just show a few things that we already started to work on a different context, though. This is a system, for example, developed in Alberto Del Bimbo's lab in Florence, and this is it's enabled by just monitoring the activity of the head, by just using the head pose to capture visual attention. Here is a project done within a cultural heritage project. So the idea is that there's a viewer watching, say, a picture or a wall in this case, and when he moves his head, the system illuminates the part where the visual attention is captured. So you see this guy here is moving his head, and visual attention is captured. So we can import these technologies, of course, within our system. Of course, things will be different, but the basic technology is still there. And yeah, I'm done. And here is another example of detecting conversational groups. These are called sometimes F formations. When people have a conversation, they usually orient their bodies in a way that they form kind of a circular shape or semicircular shape. And within my lab, in collaboration with IIT Genova and University of Amsterdam, we have developed a technique based on game theory to detect F formations in a given scenario, which is quite powerful. The accuracy is above 95%. And detection of anomalous situation, here is an example, an outdoor example of a system developed at Florence lab. So you have a street where people are just walking, and there is this car, and so the system detects that something strange is going on, an outlier, if you want to call it. Of course, we have to use this technology in an indoor environment. So, for example, we want to see whether in a corridor which is quiet, someone is running on something like that. As far as user interaction, this is a tricky part, of course, as we know already, and we're going to use, to minimize the use of audio, and we're going to use tactile or haptic interfaces, and possibly the system that is being developed in the Fifth Sense project. So conclusion and outlook. It looks like that today's computer vision technology is mature enough to allow us start in thinking of a kind of a social assistant. Of course, in a very controlled setting, working in an indoor scenario is something which makes us feel better. And you know, there are a few technological and scientific challenges that we have to deal with. Of course, accuracy and speed, and cost, of course, and usability. As James just pointed out, it is very important to get feedback from the final user, from the visual impaired person. And to this end, we are collaborating with the Italian Blind Association, in particular with Barbara Lepporini. She is the president of the Italian Blind Association Tuscany section, and she's also a researcher at the National Council of Research, working in human-computer interaction. Okay, thank you very much for your attention.
We have time for a quick question. Please, there are microphones.
Thank you very much. It was a great talk.
Thank you.
And I think it's very, very important to give people some social context, to make them feel part of the group and to understand what's going on.
That's right.
The only thing that I'm wondering about, I'm wondering how you handle this, that, okay, so you got Ruth over here, Mary over here, and of course they change places, and this person's very visually impaired. How are you going to give them the information that the person named Ruth and the person named Mary are now, you know, opposite? And I can say for myself that if there's a lot of people, yeah, I can't remember names, but I can remember you said you hate Obamacare and you said something else. That's what I remember. But so, I mean, you know, to follow, I have a way to follow. I don't need the name per se. But when they move, and just the direction of speech, I'm not sure that's enough to remember, you know, that's the one who hates Obamacare, just that was standing over there. Do you see what I'm saying?
Yeah,
so that's
sure.
my question.
Okay, thank you. I think this has to do with this problem of tracking people around. This, I guess, has to do with identity discovery, but it is more or less has to do with person re-identification and tracking. So if you have two persons over there which are moving, so the system has to solve basically a multi-target tracking problem, if I understand correctly. So. Okay, so it has to do with yeah. This is something we have to work on, of course. There's the audio information is something that we might use, but also other information concerning braille and tactile information. But this is something we have to work out. Yeah, of course. Yeah.
Okay, thank you, Marcello. And now it's time for the next speaker.
Okay.
Please set up the computer. And the next speaker will be WEILAND from the Doheny Retina Institute and the University of Southern California. And he will give us a talk about retinal prosthesis for the blind.
I want to thank you for inviting me to this great workshop. What's not in my bio in the program is that I'm the great-grandson of Madeline and Settimo Brojo, who immigrated from Torino in the early 1900s to this country. And I think that my bisnonna and bisnonu would be very proud that I was here today speaking to you about retinal prosthesis for the blind. I'm at the University of Southern California, and in addition to, this is a little bit of a different type of topic than what you're going to hear about mostly today. Mostly you're going to hear about computer vision, assistive technology, but there is a role for computer vision in retinal prosthesis, and we do have a project on computer vision. So in addition to retinal prosthesis, at the end I'm going to touch lightly on our work in computer vision and then tell you how I think they can work together. So a retinal prosthesis relies on an external camera or some type of camera to convert an image into an electrical signal. That electrical signal is then processed by electronics into an electrical pattern which can then be applied to the retina in a way that we hope provides some functional vision to the user. In this diagram you see a camera outside the body, which information is wirelessly transmitted to an implant inside the body, inside the eye, and then on the retina is a multi-electrode array, an array of metal contacts or conducting contacts, and that's where the electrical pattern is then applied to the retina. And in this case, we're looking at the letter E of the eye chart, and then the letter E is shown being applied to the surface of the retina. This is an epiretinal implant. That's mostly what I'm going to talk about today, is an implant on the surface of the retina. I also want to point out that subretinal implants are placed underneath the retina in the place of the photoreceptors. Just to give you a very quick orientation on the retina, again, this is where the photoreceptors are, the bipolar cells and ganglion cells. So an epiretinal implant will stimulate the output cells of the retina. A subretinal implant will be in the place of the photoreceptors. A quick update on the clinical status of retinal prostheses overall. 2 devices have regulatory approval. The Argus 2 has approval to be sold in Europe. It has a CE mark, and it also has approval by the FDA. The Alpha IMS, it's produced a subretinal implant produced by Retina Implant, a German company, has a CE mark. And there's been clinical trials of other devices. In general, across all these clinical trials, patients like the implants and are happy that they participate. It's not uniform, of course. You're never going to have 100% satisfaction. But in general, a vast majority of patients are positive. We find that it helps with navigation. I'll show some data. Visual acuity remains an issue for all these devices. So even with retinal prostheses, patients who receive the prostheses would still be considered blind by visual acuity measures. No one is seeing below 2200, which I believe is the standard of blindness. The best visual acuity that's been reported, and this is only in one patient, is 2560. So still fairly poor vision in terms of acuity that we can provide with retinal prostheses to date. And these devices all have challenges. So I'm going to, for the sake of time, and because this is the project I work on, I'm going to focus on the Argus 2 retinal prosthesis. It's produced by a company, Second Sight Medical Products, that we work closely with. Here's the 3 parts of the device. This is the head-worn camera. On these glasses, you can see right there is a micro camera, and by which the image is acquired. Here's another view of that visor with the camera right on the bridge of the nose. And then they wear a video processing unit. So this is a specialized wearable computing system which takes that video and converts it to digital data, which is then transmitted via an antenna on the side of the glasses, as shown here, to the implant. This is the implant down on the bottom. It's akin to a pacemaker, in which it has a case in which the electronics reside. It has a coil for power, so inductive power transfer. And then all of these parts remain outside the eye, on the side of the eye, so underneath the conjunctiva or the skin of the eye. And then the part that goes into the eye is this ribbon cable, and finally this electrode array, which has a 6x10 grid of electrodes. So when I talked about visual acuity, you can imagine going from 100 million photoreceptors down to 60 pixels is certainly, we can't expect perfect vision from that, but it's, but we're encouraged by some of the things that people are able to do. Improved mobility was demonstrated in a multi-center clinical trial, which I'll talk about in just a moment, with 30 subjects, and the subjects were also demonstrating some letter reading, which I'll show as well. I want to acknowledge the larger group that worked on this, of course. This is a multi-center trial. These are the people who worked on this, and this is just not even a complete list of everyone. So really, I'm here representing a large group. As I mentioned, 30 subjects at 10 centers. This was done, preceded by a pilot study at the University of Southern California of an Argus 1 device. All subjects are seeing phosphenes with the system. So a phosphene is an artificially generated perception of light. With the Argus 2, all the subjects were able to say, yes, I see something. All subjects have used the system at home, so it's a mobile system. And we're going to review, again, this study published by my colleague and the leader of our project at USC, Mark Humayun. It was published in the journal Ophthalmology in 2012. So some of the tasks they're able to do involve, for example, square localization. We asked them, this is a patient the task is point to the white square on the screen. It's a touch screen, so we're able to record when she points correctly to it. This is some of her data with the system off. These circles represent where she pointed versus the square, relative to the square, which is shown in the center. With the system on, she's able to point much more closely to that square. So you could imagine, this is a very lab scenario, very contrived scenario. But you can imagine if we could use computer vision to turn a desired object into a square, that person would then be able to have the hand-eye coordination to reach out and grab that object. And I'll show some examples of how we might do that later. So the fact that they're able to get hand-eye coordination is in fact very important and encouraging for a reach and grasp type of task. And this is the data across all 28 subjects that we could test with this task. A lower number is better. That means they were closer to the center of the square. So you can see with the system on, which are the black filled squares, they score better in 27 out of 28 subjects. So most of the subjects, almost all the subjects, were able to obtain this hand-eye coordination using this device. A big task that blind people tell us that they'd like to be able to perform better is orientation and mobility. And so we arranged what we call a door task and a line task. This isn't really a door. This is just a large piece of black cloth against a wall, but it's about the size of the door, and it's in an environment in which you might want to find a door. And initially, we started the folks in one of 3 locations and kept the door in the same place. But as with any type of experiment involving a biological system, they adapted to be able to find the location of that door even without the system. They were able to learn, go here, based on other environmental cues. So then we started moving the location of the door around afterwards. Similarly, a straight line, we asked them to walk a straight line using the device and without the device. And we eventually added corners to the line to make it more difficult. Here's some of the data that we found, and you'll see that this is where they started getting good with the door task without the system. So red is system off, blue is system on. They're able to find this door much better with the system on versus the system off. And this is the point at which we started moving the door location around, and you can see that their ability to find the door decreased significantly after that with the system off. Yet with the system on, they were able to, again, find that quite well. The line test, they're able to follow up. Blue is with the system, with the Argus 2 device. Red is when they don't have the system activated and they try and perform the task. They're able to follow a line much more successfully when using the Argus 2, between 75 to, well, 82 to 54% success. Okay, so that was some data that I went through rather quickly. I think sometimes it's more instructive to show videos of what the patients are doing. However, I did want to show you that data to show you that we did do comprehensive testing across a wide number of subjects. So this is a subject at USC whose task is to follow this line. What you'll notice about this is that she's able to localize it, point to it. She strays to the right a little bit, then corrects herself, and also she finds the end of the line. So it's not that she's just good at walking a straight line. And other things I'll point out here, you can see this is the video processing unit, so she wears that on a strap. There shouldn't be any audio with this, so we don't need to turn it up if that's, thank you though. We will have audio for the next video. Here she starts to drift to the right a little bit. Again, in terms of testing, we started with tape on the floor, but they were able to feel that with their feet, right? So we needed to switch to painted tiles, they didn't get a tactile feedback, which they got no tactile feedback from. She finds the end, and then she stops. And I'll point out here, here we ask her to do it with the system off. And here you see the gesture of someone not knowing what to do, where she throws her hands up, very similar to the last talk, right? So we ask her to follow this line without the system, and she says, I don't know, I don't think I can follow it, see? She puts her hands up. There's the gesture we were just talking about in the last talk, and she just goes off and tries to walk a straight line, but of course she can't. I do like to point out that we do stop her before she hits the wall in this case. Subject safety is, of course, very important. This is a Paris subject, so we'll need audio for this part. He's going to be reading these numbers that he's holding in his hand. So he's using the camera of the Argus 2.
Le 9, je pense.
Oui, 9.
D'accord. C'est bon, ça. Ça, c'est le 5, je pense.
Oui, 5.
So this video isn't cut. You see it takes him several seconds in order to make this determination. He's one of the better subjects at doing this.
On verra exactement ce que voilà, ça c'est le 3.
Oui, 3. Correct.
So again, he's one of the better subjects. Typically, it will take 10 to 20 seconds for the subjects who can read letters or numbers to do that. We can argue about whether that's reading or not. It might be better considered more form recognition versus reading, which isn't really a conscious effort. We just look at that and we know what the number is. We don't, for example, the number 4, we don't think, oh, there's a diagonal and there's a line, at least not consciously. We just know it's a 4, right? Nevertheless, I think this represents good progress and hope for the future that we can, with training and learning, we can achieve this. Okay, so now I want to show another video of a subject using this in out in the wild. I think that's a great term that Seth used earlier, where it's not the lab environment, but in fact, what he's doing, he still has his cane. I don't think we're going to be taking the cane away from folks anytime soon, nor do I think we should. It's it's a safety factor, and it's a very useful instrument that helps keep you out of immediate trouble. Nevertheless, so he's using his cane still, but what he's doing is he's looking at this drain in the plaza here and looking at that line, and he's able to use that to walk a straight line. And I would challenge you in this room to just close your eyes in a safe environment, of course, and try and walk a straight line. And then open your eyes after 20 steps and see how straight you walked. And you'll find that you probably didn't walk very straight. So even having that cue, being able to use the retinal prosthesis to detect the contrast and follow that line is a benefit to mobility. You'll also see that when another pedestrian walks in front of him, he's able to stop. A little bit late, so I think we need some predictive software in here. But see, this gentleman walks in front of him, and then he stops. And also that he's able to find the end of the line. So again, imagine if he knows that his apartment door is at the end of this line, he can then know, I'm home. I've reached the end of that, and I'm quite confident that I'm home. So there's many of these cues, as was pointed out again in Seth's talk, that exist in the environment. And even with a little bit of vision, we think that the retinal prosthesis can help people take advantage of these.
Bravo.
Okay, so I want to summarize the Argus 2 clinical status then. Across all patients, there's 140 implant years. This goes towards safety. 2 implants have failed and 3 devices were explanted. 2 of them elective, 1 for recurrent conjunctival erosion. So again, that's the skin of the eye. You can imagine implanting a large device may cause some abrasion of that skin of the eye. And if that continues to break down, we have to take the device out. Otherwise, it becomes an infection risk. Again, subjects generally like the device. It has CE mark and FDA approval. And there have been 40 commercial implants, and I want to point out, again, a connection to Italy, that Stanislao Rizzo, who I believe was at the Pisa workshop, is the leading implant surgeon, and not in Italy, in the world, really. It's the leading commercial center for these type of implants. As of October 1, in the United States, CMS, which is a body which leads to insurance payment for these devices, approved new tech add-on and translational pass-through. I don't know what these words mean. These are important for people who decide whether insurance is going to pay for the device. If there's MDs in the crowd, they could probably, they're nodding their head, yes, they know. But the point is that this is a good step towards this being paid for by insurance, which is critical to the success of any medical device. So research areas we're working on, we want to generally improve the quality of the visual experience, provide peripheral vision. I'm going to focus on using computer vision to emphasize important areas of the scene. I think a critical area also is brain mapping. We're going to talk a little bit about what are the brains of blind people like and how are they different. The Argus 2 is actually MRI compatible. We've developed experimental paradigms by which we can activate it in the scanner, and we have IRB approval to do that, and we're getting ready to do that with some of the first implant patients in Los Angeles. Okay, so I've got a little bit of time left, so I'm going to talk now about our work on the wearable visual aid, which is, I don't need to tell you how this works because there's been 3 talks already about this type of system. The user would control a smartphone, and then the scene would be captured by a head-worn camera. I strongly think that a head-worn camera is critical to the success of these types of devices. We point our head to give ourselves direction. We scan scenes by moving our head around naturally, and I think that would be the exact same situation for someone using a wearable visual aid. So I think James was correct in bringing that up as a point of discussion. And then we use either wearable or cloud resources to do the computation. I think interaction, having the person control the device through a smartphone is really also the way to go. So I'll just show you some of the things we've done here. I want to point out my collaborators, Gerard Medioni, Laurent Itti, Armand Tanguay. This collaboration made me think that computer vision was the province of the French, but now I know, coming here, that the Italians are very strong in it as well, and I'm glad to know that it's not only a French endeavor. About 5 or 6 years ago, I started working with, 7, 8 years ago, I started working with Gerard Medioni, and this is an example of our project. So this is done at the Braille Institute, Los Angeles. This woman is completely blind. She's wearing a stereo camera, commercially produced by Bumblebee, or this might be the Tizix stereo camera. Anyways, it's a depth camera that gives you depth information. And Seth talked about earlier about the SLAM algorithms. This is implementing a SLAM algorithm and providing cues to the person through vibration motors that she has on a vest. So it's vibrating left or right, and that guides her through this environment. And it's running closed loop, and she's able to walk through here without the guide of her cane, only using the vibration motors that are on the vest. You see the walking's not really crisp. We have someone walking behind her for safety. So there's this kind of rectangular type of walking that's going on, because when we tell them to turn left, they make a 90-degree turn left. So there might be some training that would be needed in order to get these people to make a natural sense of walking and to impart them. That's a control problem. So again, I was glad to know that there's people in control theory here who are maybe can see now some of the areas in which that need to be worked on. We need to guide them on a smooth path. Okay, so that was some of the work we've done on mobility. So again, this is not, I'm away from retinal prostheses now. This is the wearable visual aid. In this task, what we've asked this person to do, we have a wide field camera which is viewing these objects, and we're not identifying the object yet. All we're doing is highlighting it. So an operator, an experimenter on this laptop is picking an object for the person to find. And I think they're going to pick this red box of cream of wheat cereal. We provide to them through bone conduction headphones. So we're not occupying the auditory channels. We have bone conduction headphones, which is a nice technology and actually works quite well. We tell them left, left, left until they've centered the camera over the object that we want them to acquire, and then we tell them center. And they'll, again, using their their proprioceptive sense of, I know where my head's pointed, and I'm going to reach right out in front of that, they're able to acquire the object. This is, again, with a blind user done at the Braille Institute, Los Angeles. You'll see that he's getting commands. He's able to move his head towards the object. You can follow the movement on the laptop screen here. He's centered the object, and he's able to reach out and touch it. Finally, Laura made a very nice description of a scenario where a user would have a smartphone interface that would allow them to specify what they wanted to do. I must tell you that the scenario we've created isn't as romantic or inspiring as yours, but what we've asked this person to do is find this box of Splenda on the bookshelf, and I'll show. Could we have audio actually on this one, please? And we do have a smartphone, not by this user, and this is a sighted person, just one of the students in the lab, but we do select the object from a list. So we have a smartphone interface where we can select an object from a list, do object recognition, direct the person to point the camera at the object, and then finally grasp it. So this is a prototype of an end-to-end system where a user would want something, and then they'd find it, the system would find it, and then they'd be directed how to grasp it. So this is what the camera is seeing. There's the box of Splenda. It's a sweetener. So we select it on the smartphone. That communicates to a laptop.
Splenda sent.
And we use a object recognition system called SURF, which is well known.
Attention biasing.
But what we've done is we use attention biasing. So we look for salient parts of the image, and we only perform the object recognition on only portions of the image, and that speeds it up. So there's the audio instructions, which are certainly not optimal. Stay, we're telling him stay. So we can work on that, right? It's, but he's able to reach and grasp it. Yeah, so we definitely need to work on the audio that we present. Guilty, all right? We have engineers designing this, and it's, okay, so we need to fix that. But that's easy. That's easy to do. So that was success, but I want to echo the point that James made about the brittleness of these algorithms. This is a Splenda box that we were using, and the object recognition was trained on that box. I went to buy some more, because when you go to a grocery store, you'll see multiple objects together. So I picked some Splenda off the shelf, which I easily recognized as Splenda. And we tried running it with the Splenda boxes that I brought in, and it completely failed. And the reason is they changed the pie. They changed the picture of the pie on the Splenda box, and our object recognition program completely failed after that. So these are brittle algorithms, all right? And that's a major, major impediment. And it was, I had no idea. I just saw Splenda and I grabbed it because I knew it was Splenda, right? Because we know that. That's easy for us. It's very hard for computers, and we have to figure out how to do better. Okay, that is it. I think that the retinal prostheses are certainly showing promise to restore partial vision in cases of severe retinitis pigmentosa. Only partial vision, but a little bit of vision goes a really long way. I mean, I would say, imagine the scenario where all the lights in this room became completely dark except for the exit sign. I would say most of us could use that one little bit of visual information to exit the room. So I think a little bit of light can provide a very strong cue. And if we couple that, this doesn't have to be an either-or thing. If we couple that with computer vision to figure out what's important to the person right now and how can I help them, either with auditory feedback, with the partial vision that we can provide with the retinal prosthesis, with tactile feedback, I think that we can really make a lot of strides towards our joint goal of helping people with visual impairment. Thank you.
Set? Yes, please.
Mind-blowingly cool and fantastic. I don't have enough adjectives to say how cool that work is.
Thank you.
Two quick questions. One is, can you comment on subjective adaptation to this thing analogous to the way people with new cochlear implants describe a sense-making process of a year or two after they start to get hearing and turn indistinguishable sounds into salient stimuli? And second, the fellow who was reading the numerals was doing the scanning with a certain time constant.
Right.
What was he doing, and can you facilitate that upstream of the implant so to make it happen for free?
Sure. So regarding learning, we don't have strong evidence of learning like in the cochlear implant. The stories I hear from cochlear implant patients is that the words they use is, I don't have to think about it, I'm just hearing it. Right? They hear and they understand. We think there's still a cognitive step involved in, certainly in the letter reading right now. I think there may be a little more learned effort or learned ability in terms of mobility. And then the second one was the scanning. Yes, because it's a fixed camera, so in order to get spatial information at this point, they need to scan the camera over the scene. We haven't examined in great detail the patterns that they move the camera in, the time constants, those kind of.
He was doing it at a smaller range of angle than the field of view, so it looked like he was actually doing some sort of spatial temporal integration over the features in the letter.
Probably, and he probably had certain electrodes which worked better than others and gave him better spatial information than others, and he learned to use those in order to accomplish this task. So I think there is probably some learning going on. We need to study that some more, and we have the system now that we can do that with.
Thank you, James. Okay, the next speaker is A.BICCHI from University of Pisa and also Istituto Italiano di Tecnologia, Italian Institute of Technology. And he will give us a presentation on what do the eye and the hand tell us about the brain and how this can be useful to people. And this work is a joint work with Pietrini, Ricciardi, and Santello.
Hello. Yeah, so the talk is about what the eye and the hand tell us about the brain. And this is joint work with Emiliano Ricciardi, Pietro Pietrini, and Marco Santello. They are from Emiliano and Pietro are from the University of Pisa. Marco Santello is from Arizona State University. They are all neuroscientists. I am an engineer. I am the one who programs stupid audio feedback in applications. The talk is about the interaction of these two disciplines and how we can help. So the eye is definitely one of the most marvelous parts of our body, and we have seen in the great talk before what is the complexity and what is the technology that is being developed to help people. The complexity of the eye is definitely amazing. also the complexity of the hand is not to be underestimated. The hand is made of many bones, many veins, arteries. The ligaments and muscles are in a large number, and they are complexly connected. Tendons, nerves, and the skin itself is a tremendous source of information, very complex, very articulated information. How can technology match the complexity, the challenge of this complexity to help people? It's, we have been working for a long time in trying to replace or substitute or help people with one of those senses, and it's really the challenge is this complexity. So the idea was, why don't we look at how the human brain can cope with that? I think I can, yeah. The idea then is to look at the body, and maybe the body is not just a cage for our mind. Maybe the body is a dominating factor in determining how cognition has evolved in the admirable form we know. And the constraints that the body imposes are really what define us and enable us. So the idea is to put together engineering and neuroscience together to understand, to build better devices, but also to build devices in order to understand better. So the complexity, how can we make sense of all this complexity? One of the typical things we try to do is compression and abstraction. And in vision, this is an old thing. All the artificial vision hinges about, or most of it, on how you can reduce data for sensing, displaying, or communicating, extract information from an image, extract information from sequences. But questions are, how do we conceptualize what we see? How we close the sensory motor loops that imply decisions, and often how we do this quickly in short time enough to make, to avoid bumping into obstacles, for instance. So this is an example of what I mean by this process of abstractions of the optic flow. Optic flow associates incremental changes in image with motion of objects relative to camera. In human and artificial vision, optic flow is crucial to fast sensory motor feedback. Now, when we look at the images, we have several layers of processing. Of course, there is face recognition, there is reading, but at a lower level, at a much faster level, there is the need to avoid obstacles, to chase, and at the ecological level, to chase for prey or to run from predators. And optic flow is a very simple abstraction of images that comes much faster and much before any conscious processing. And the optic flow is a processor that is sort of wired in the brain. So if you have objects that move in your image, then you have parts of the brain in the cortex, in the area V5 and T, that respond selectively to components of optic flow. There are other analogous phenomena in the hand. Again, how the complexity is organized. And here is a work that comes from Marco Santello and several other workers in the hand motor system. How do we control a hand that is such a complex system of motors, for instance, so that we can make easy use without thinking of the coordination? Now, there is evidence that there exist sensory motor synergies or primitives or constraints that organize the system. And here is one way of describing this. In a statistical analysis of how humans normally use the hand, you can find that there are modes that are here depicted as the columns of this matrix that are the principal components, the most often used modes that explain most of the covariance of the hand motion. So the first synergy alone, for instance, explains more than 50% of the covariance more than half of the times we use the hand, we use one basic motion, which is this one, very simple one. And the first, second, and third together make 90% of our grasping abilities. So it is possible to abstract complexity in a principal way by reducing to more elementary features. Of course, to be able to use the hand in all its richness, you need all the synergies. But to do some approximation, you might use a few. So to what extent is it possible to convey vision information through touch? And what are the mechanisms that underpin sensory substitution? The classical approach to this is basically cross-modality. The sketch is very rough here, but you can think there should be a hand that didn't show. Yeah, sorry. There is a hand that didn't show, sorry. So in cross-modality, you sort of rewire the information that used to come from the eye with something that would come from the hand, for instance. And you rewire, you retrain the person to do this. But another approach is the supramodality. And I will talk a little bit about this, because this is something that the group in Pisa, especially, Pietrini and Ricciardi, have been investigating for many years, that is providing a lot of insight and useful hints to us. So the supramodality means that there are structures in the brain that are in common to both these and probably other sensory channels. Again, these results come from long experience with functional MRI with blind people. But while most of the research in blind individuals classically has focused on the compensatory plastic rearrangements that follow loss of sight, especially in early visual areas, then the more recent functional brain studies in both sighted and congenitally blind individuals showed the existence of a supramodal brain region that processes external information independently from the sensor modality through which the information has been acquired. And then it postulates a more abstract nature of functional cortical organization that might enable congenitally blind individuals to acquire knowledge, form mental representations, and interact effectively with an external world that they've never seen. And here are some experiments we did on exploring this idea. So coming back to flow, we applied the hypothesis that there is also a counterpart in tactile flow. Flow is a dynamic sense, just no less than vision is a dynamic sense. And we have information from how the pattern of our cutaneous information changes in time. And we derive information about the relative motion of the hand and the object from these changes. So we asked people, and we had subjects under fMRI, to touch objects that would translate or rotate or have a radial flow of tactile. And then these areas were correlated. And both visual and non-visual motion perception not only share fundamental psychophysical aspects, but also recruit a specific circuit within the middle temporal cortex in both sighted and congenitally blind individuals. So in other senses, tactile flow was shown to explain the counterpart of common visual illusions. Illusions are very important to understand a sense. And in these studies, we could show that coherent changes in visual images caused by object or viewer movement are providing information about object form, position, and movement. So this led us to develop better haptic devices, which I will not deal with. We have seen many haptic devices here. I will spend more time on other subjects this day. Supramodality was investigated by Pietro and Emiliano in other contexts. Supramodality for several perceptual and cognitive functions, spatial orientation, tool use, voice perception, object shape recognition. This is definitely not just touch and vision, but also auditory. And similar cortical networks were seen to subtend visual and non-visual perception of form, tool, space, and motion. Also, affective and social life have a supramental representation in the brain. So, for instance, in this example here, sorry, no, I have, okay. So the no, okay. The question comes to mind: to what extent is vision really necessary for the human brain to develop and function? And some quite thought-provoking thoughts come from the study of congenitally blind people. Here are pictures taken by a non-blind photographer. And here is something that I found very puzzling. This is, you probably know, Ezref Armagan is a Turkish congenitally blind painter who is able to have these paintings. Then this supramodal mirror system for actions is able to convey information that you would think would only come from vision. Blind individuals, for instance, response to an action sounds overlapped with the mirror system of sighted. So the same areas are basically activated when you see someone knocking a door or when you hear the sound. Even for the congenitally blind, have a strong correlated area to those of a normally sighted person. So visual experience might not be necessary for the development of an efficient social brain, of course. This and other studies were supported by the Blind Brain organization that is led by Pietro Pietrini. And there was recently a very interesting workshop in Pisa where some of the people in the audience also participated on this subject. Let's go back now to synergies and the hand system. Also, the hand system seems to have strong correlates in the images that we have recently obtained from the brain. And how does this impact the design of technology? So now let's go a little bit to a different field than vision. Now we are talking about hands, and we are talking about the problem of other people with different disabilities than visual, people that have lost their hands. And what is the problem with prostheses for people? The technologies of robot hands is there. We have very sophisticated hands already. The real problem is that they're too sophisticated. They're not robust enough. They're not affordable enough. And the problem is simplification. Unfortunately, simplification is not easy. So the same way as with vision, if we look for structures that may allow us to simplify in a principled way the design of hands, that might be a very useful to people. So the real problem is how to make hands that are soft yet strong, simple yet dexterous, intelligent yet practical. And the approach that we have followed is using some soft robotics technology and this theory of human synergies that come from neuroscience, again, putting them together in building a device. And I will show in the final part of the talk some results about this Pisa IIT soft hand that we have developed recently. So the idea of synergies is put here into the context. You have this hand that moves and grasps an object. Now, synergy basically means that the hand moves in a coordinated way. And this hand is only using one synergy. So it's moving with 1 degree of freedom. All joints move together in one pattern. The problem of grasping an object and controlling the grasp forces has to be introduces a problem with the control of forces. And this can be solved by introducing this soft actuation idea. Basically, so the conjecture is that the brain is controlling the inner representation of the hand along the synergy manifold, but the real hand complies with the object. And through this attraction towards the virtual image of the hand and the repulsion from the contact forces with the object, a force and an equilibrium is reached. So not only the idea and the synergy idea is needed, but also you need some innovative design for affordability and robustness. And here is some of these ideas that come basically from observation of the human or natural articulation and bones. So these are fingers that are no bearings and have elastic ligaments. They can resist impacts. Affordability and robustness are overall, the most important things if you want to do something for helping really helping people. And here is the hand that we built that can resist this kind of impacts. The hand is built with this idea of synergies so that it can grab many different objects. As you can see, the shape of the hand adapts to the object. One of the most important things in doing prosthesis is that you have to make it simple to control. By large, the most common reason for abandoning a prosthesis is the complexity and the fatigue that the person finds in controlling the hand. This hand was doing all the adaptation that you've seen with only one motor and one input. It's really by embedding this synergy idea into the mechanics that the many different grasps were possible. Yep, I'm finishing. So here is the hand that has been used for some grasp by a person wearing it. As you can see, the person only controls one bit of information, open and close. And the hand can help her in different tasks. Here are a few more. Here are a group of children who were using the hand. And it was very interesting to see how ingeniously they could use the hand. The girl could pick a coin out from a table in a very natural way. It was really amazing how their brain could adapt to the use of a very simple device to do things that we would never think the hand could do. And the hand is a candidate for being a prosthetic device, of course, so we are working now on this perspective. So here is another support for the hand. Now the human hand does not control any mechanical device. We only use EMGs to control the hand. And with EMG control, you can do control, you can grasp soft objects or rather heavy objects like the second or even the third one, which is rather heavy, is half a kilogram. You adapt the stiffness of the hand to the task. Still, the hand is very simple to control. Only two muscles are used. So the hand can be both precise, accurate, delicate, as for instance in grasping a strawberry or a noodle, but also pretty strong. And in the video on the left, in the end, it will tighten up a coffee making machine. And it is interesting to me to say that most of this came out of the collaboration with our colleagues, neuroscientists, who really provided the key enabling idea that was this complexity reduction idea that we saw at the beginning. So with this, I would like to thank all the collaborators from our groups that helped us in this work. And if there are any questions, I'd be happy to answer.
Questions? If there are no questions, please, Zaira, come. And there will be occasion to discuss with Antonio also during lunch.
How do you open it? Wait.
Where is the technician? He's coming. Okay, next speaker is Zaira Cattaneo from the University of Milano-Bicocca, Italy. And she will present blind vision, perceptual and cognitive functioning in the blind. Again, to all the speakers, if they can stick to the 20 minutes, it would be better, or less. Because we are late.
Okay, so thank you so much for the invitation. So I go directly to the talk, so I try to be as brief as possible. So basically my talk falls a bit on the other side. So we had engineers, I'm more, definitely more on the neuroscience part, and even more on the behavioral psychological part. So I will try to make the talk as general as possible, because I understand that the audience is different than the audience I'm used to in other conferences. So basically what this slide shows is the fact that as humans, we rely on a multiple sensorial information. So we have information from our hearing, from sight, from our taste, of course, and as we have seen in the previous talk, all the sensory motor information is fundamental for the experience that we have of our world. So, but what happens when one of these senses is missing? Here we have a few examples. Of course, Stevie Wonder, that is blind, or Beethoven, that was actually deaf, or the writer Helen Keller, that incredibly was deaf-blind, and she was still able to achieve so much in her life, or the case of the athletes there that miss the legs. And so what happened to the brain of these people, and what happened to the way they represent the external world? So our brain is able to cope with this different sensorial information when one information is missing. So here, today, I would like to talk more, of course, about the blind, but we have also investigated the case of deaf individuals, so I will maybe give you also some information about deafness. So blind individuals can acquire information about the external world only by the hearing and by touch. So given this different way information is acquired, is the way the external objects are represented in the brain the same as in case of sighted individuals, or are there any differences, any substantial differences? So we started considering what happens in case of normally sighted individuals. So in case of normally sighted individuals, there are strong biases in the way we represent space. Maybe we are not aware of this, but most of us tend to have an overrepresentation of the left part of the space. So this is a classical test used to test this. So basically, if I ask you, either in the visual modality or also in the haptic modality, so blindfold and just doing this, to tell me what is the midpoint of the line, what most of us usually do is to bisect slightly to the left. So this is the true midline. And what we tend to do, now here it's exaggerated, but not so much actually, is that we tend to bisect more to the left. So why this is the case? So basically, this is the case because we have two hemispheres, of course, in our brain, and the right hemisphere is more important in spatial processing. So the right hemisphere controls the left part of space. So what it happens is basically that the left part of the external space is somehow overrepresented, or it's there are different interpretations, but to make it short, basically, we either pay more attention to the left, or the left part of space is somehow expanded. So that's why we tend to bisect to the left, because this means that for us, the left part of space is equal to the right part, whereas indeed this is not the case. And so our question was, okay, well, is also the case of blind individuals? So do also blind individuals have this hemispheric asymmetry for which they tend to pay more attention or to overrepresent the left part of space? So we did the same task with blind individuals. We did it in the horizontal plane, so asked them to bisect a horizontal rod, but also in the vertical plane and in the radial plane. So now, since I have to be short, I will just focus on the horizontal plane. So this is the experimental setting. So basically, here you see in case we had, of course, also control participants that were sighted, individuals that were blindfolded. And we asked participants to touch the rod and to tell us what was the exact midline. And they had 10 seconds to do this. And basically, what you can see here, I point, sorry, to the right graph only. So basically, in the horizontal plane, what you can see here is the deviation from the true midline. So 0 means exact midpoint. So everything that is negative means that participants deviated toward the left. So basically, as you can see, both blind individuals, that is the dark gray and the light gray is sighted, so both blind and sighted participants tend to bisect significantly toward the left. So this means that blind participants show, at least in the horizontal plane, a similar bias as sighted individuals. So their brain, in other words, represents space in a quite similar way, at least in this case. I mean, they also have right hemisphere dominance in spatial processing. So I told you before that we also investigated other sensory deprivation, so I just wanted to show you this slide. Here is the case of deaf individuals. So usually when you test deaf, you distinguish between two groups. So deaf signers that use sign language and deaf non-signers that use lip reading to communicate and to understand what other people are saying. And both groups, compared to our hearing contours, show with no pseudo-neglect. So pseudo-neglect, maybe I didn't say it before, is this tendency to bisect to the left, to overrepresent the left side of space. So basically, deaf individuals seem not to have this. So in this case, another sensory deprivation seems to modify the hemispheric balance in the control of spatial attention. And why this is the case for deaf? Well, our interpretation is that sign language is very spatial. So it activates more, so the left hemisphere that is responsible for language gets also more activated by sign language. So it becomes more spatial also. And why is this the case also for deaf non-signers? Well, this is still an open question. We are trying to understand it. But one hypothesis is that when deaf non-signers try to understand what the other person is saying, it focuses the attention toward the center. And this might somehow balance more the way attention is distributed in the space. And since we are at the Bocelli Foundation, I want also to talk about musicians, because we have also tested them. You know, sensory deprivation and training are two ways to get into the way the brain functions, so into cortical plasticity phenomena. So there are both ways to understand what is happening in the brain when something is missing or when you work intensively on something. So, and what happens in case of musicians using this task is basically that they bisect to the right. So this work was done by Patson and colleagues in the visual modality, and you see that they tend to deviate toward the right. And we have done also the same thing in the haptic modality, and still they deviate to the right. And it does not depend on the instrument they play, so it's not just pianists, but even if they play, I don't know, another instrument, saxophone for instance, it works anyway. And here the idea again is related to the language that musicians learn to use intensively, that is the musical language. So music, as you can see here, so notes are a very spatial language. So basically, again, language, the semantic content of the note is related to a spatial distribution of the notes on the lines. And so basically, space and language go together, and the left hemisphere becomes specialized also in spatial processing. So that's the idea behind. So far I've discussed this attentional asymmetry in case of a perceptual task. So you see a line if you are deaf, or you touch a line if you are blind. But we can also think about something that is more placed at a more representational level, so purely representational, that does not depend specifically on touching or viewing something. And for instance, a typical paradigm that is used to test our pure mental representation of space is numerical bisection. So I don't know if you are aware, but basically we as Western, at least citizens, I mean people that live in left to right, that write from left to right, we tend to represent number in as distributed on a number line. So basically the low numbers are placed to the left. So if I count, I tend to think 1, 2, 3, 4, 5, so they go this direction. And what it has been found is that if you ask someone to tell the middle of two numbers, for instance, if I ask you, tell me what is in the middle of 15 and 26, without counting, so you don't have to count, of course, otherwise it's too easy. You just have to guess as soon as you can what's the number that is in the middle. What you usually do is that you tell me a number that is more to the left, so lower than the real mid number. So this means that even in a pure spatial mental representation, that is the way we represent numbers, we have this left bias. And this is very systematic and very consistent. And also it's very strange, I have to tell you, that we think we are kind of accurate in this task, but it's very demanding at the end, because people sometimes even give numbers that fall outside the intervals. But it's interesting. So we did the same task also with the blind, to see if also blind represent the numbers the same way. Numerical cognition, is an important feature of learning in educational program for the children. So to teach math efficiently also to blind children, it's important that we know how they represent numerical magnitudes, not just numbers, but also other concepts like this is heavier than something else, this is taller. So it's a really important aspect to consider. And what we found using the same paradigm as the one I told you just now is that also blind participants tend to bisect to the left of the veridical midpoint. Now here you see that numbers were presented both in ascending order and in descending order, and usually what happens also with sighted individuals is that if you present the numbers in descending order, like 90, 83, well, this is easy, but 90, I don't know, 72, they tend to go more to the left than if you present the same number in the ascending order, because so the pseudo neglect becomes even stronger. Not only this, but the way we represent space on the basis of our perception and the way we represent numbers at it's a higher level of representation. These different representations that we have of space and of numbers are known to strongly interact. So for instance, this is an experiment, I need not do it, other groups now, I don't remember the authors, but basically what they found is that if you ask a person to bisect a string of numbers, so in case of 2, they tend to bisect more to the left than in case of 9. Because again, the 2 seems to shift your attention more to the left, and a higher number shifts your attention more to the right. And this is very, it occurs very systematically. There are different paradigms that provided the same pattern. So we ask ourselves, well, is this the case also of blind individuals? Because our idea is really go to see if the blind brain represents space the same way sighted individuals do, because it's really important then for the application, for the more practical application that this can have, for instance, with engineers, prostheses, and other devices. So what we did was to repeat the same bisection experiment, but this time participants were also hearing something, and it could be either the number 2, repeated like 2, 2, 2, 2, or the number 9, 9, 9, 9, 9, or a neutral string that was just blah, 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 blah. And what we saw is that, here you see again both blind and sighted participants' performance. So basically, compared to the blah condition, that was our baseline condition that you see corresponds to the 0, basically, when they listen to the number 2, their error shifted again more to the left. and when they listened to the number 9, they shifted more to the right. So this means that also in case of blind participants, there is a modulation between different levels in which space is represented. So basically, numbers can affect space, perceptual space. And there is also evidence, I have not reported it here now, but that also space perception might affect the way we represent numbers. So it's really an interaction between different levels. So this was a part of our experiment, so investigating how space is represented in the blind, so how the two hemispheres interact, and there is evidence that also in the blind, the right hemisphere is playing a major role in spatial processing, and that also blind have numbers represented the same way blind sighted individuals have, and this, as I said, is important for teaching, learning, and training, especially children. Still in this area of research, we were interested in see whether blind individuals also group information and represent perceptual information, salient perceptual information, the same way sighted individuals do. So something that is very striking in the way normally sighted individuals perceive the world is how fast and accurately they can perceive symmetry, especially bilateral mirror symmetry. And this is quite intuitive if you think about it, because faces, for instance, are super symmetrical, but also buildings are usually symmetrical, and trees and other entities in the world are really symmetrical. So our brain is absolutely sensitive to detect symmetry, and it can do it in just a few milliseconds. It's incredible. And so we decided to investigate whether also blind individuals have the same ability or the same sensitivity in a way to detect symmetry. So is symmetry somehow an innate principle of spatial organization that does not depend on the fact to have sight or not? Of course, we had to test it in the haptic modality, so we prepared some matrices here that could be either vertical symmetric, horizontally symmetric, or non-symmetric. And we did not inform our participants that symmetry was a feature of the task, also because I have to tell you, many blind individuals do not have a clear concept of what symmetry is. I mean, they can, of course, explain what it is, but it's not immediate as in our case. So what we found is that, indeed, in case of sighted participants, replicating what is usually found in the visual modality, so matrices that were vertically symmetric were remembered much better than matrices that were horizontally symmetric or non-symmetric. Symmetry was an advantage in all cases. You see here that both vertical and horizontal symmetry, this is the accuracy, memory accuracy, were remembered much better than non-symmetric ones. And what happens in case of the blind participants is that symmetry overall is an advantage for memory, but there is no difference between vertical and horizontal. So this tells us something important, that basically the blind brain is able to adopt these grouping principles of spatial organization, you know, all the Gestalt story and proximity, symmetry, there are all important grouping cues. But there is something specific for vertical symmetry that is not in the blind brain. So the salience of the vertical symmetry is not there. And now, together with Professor Mera Beta at Harvard Medical School, that will give a talk later, so we I jump directly to this, to scan our participants were during this task. So basically we have to adapt the task. Now we use a dot here. This is a very complicated system. I tried it yesterday for the first time. For me it was just impossible, but it seems that after a training session, also sighted individuals are able to do this task. Basically, so according to the position of the dots, you can obtain non-symmetric or vertical or horizontal symmetric dots. And what you see is that, I'm not sure how much you're familiar with these images, but I tried to make it as simple as possible. So basically this is the view of the brain. So this is the left dorsal part of the brain, the right. And this is like cutting the brain in the middle, opening it and look inside. So the medial surface for, again, the two hemispheres. And here the sighted group show activation that are usually found also in case of visual symmetry perception. But 2 minutes, okay. And yeah, I'm almost done. And here you see what happens in case of congenitally blind individuals. So what is interesting here, I cannot go in details, but I just want to show you this. Here there is no, and here there is. So what is this? This is V1. V1 is the straight cortex. So it's basically the visual, the purely most important visual part of the cortex we have to process visual information. So it's active in the blind. It's not active in the sighted participants during this task. What does it mean? That it's about the cross-modal mechanism that Professor A.BICCHI was telling us before. So basically, in case of blind participants, the visual cortex is recruited to process information that comes in different modalities, especially when there is a task complexity, as in this case. So basically, the visual cortex is not used because you are blind. It's super used, and it allows you to compensate for the lack of sight. So it's really impressive how the brain can reorganize, and not just in case of blindness, or in case of deafness, or in case of intense musical training, for instance, as we saw before. So I just want to summarize this. I will not talk about imagery because there is no time, but so I just want to tell you that from our point of view, from the results of our research, what it emerges as a pattern is that the blind represent space in a different way, but not in such a different way. So let me give you to this slide that is the most important one for me. So what I want to, the message I wanted to convey is that blindness is not necessarily less, but it's just something different. So what is important for us is to understand how to test the way, and how to understand the way blind individuals represent and process information at different levels, so perceptual, cognitive levels, because it's extremely important to have this information in case of children, for instance. So the idea is to develop, now we are thinking about this, to develop specific tools at school for children, because very often their abilities are undetected. And we think that they can perform less, that they perform less because they are blind, but the truth is that many times they perform less compared to the other sighted children because we don't have the right tools to test their abilities. So understanding how the blind represent space, represent objects, and process the information that comes to them from the other senses, it's absolutely important also to potentiate basically the abilities of visually impaired children that otherwise go completely, hyperestimated. And this is really a pity, especially, now we are in a developed country, so we should really make an effort. So, thank you.
We have time for just a quick question, if any. Please. And during the question, if the next speaker can come and set up his computer.
Thank you, that was great. I did want to ask, have you, I know this is, down the road, it's upstream, but have you thought about using these things, especially in children who may have or who have undetected issues like dyslexia and other impairments, though they're not blind, but we don't know what's going on in their brain either, and it's not what goes on in what we consider a normal brain?
You mean children that are not blind, but they have this kind? This is a super interesting question, and basically I've worked on it with Professor Lea Ivarinen in Helsinki that works with cortical visual impairment, and she has the case of some children whose visual acuity is basically fine, but they have extreme big problems in reading, for instance. And this is a challenge. We are trying to understand how to use our knowledge collected with the peripheral blindness to understand whether some kind of cortical blindness might have the same effects. And for, maybe Professor Meravet also will talk about this later, how the brain faces with different kind of deficits, not just peripheral blindness, but also cortical visual impairment, because sometimes dyslexia and other kind of disease are also related to some undetected cortical problems. So thank you for your question.
Okay. And let me introduce next speaker. The last speaker of the morning is Professor R.MANDUCHI from University of California at Santa Cruz, and he will give us a talk on computer vision without sight.
So I'm the last speaker, so as much time as I want, right?
No.
I love
No
captive
time.
audiences.
No time.
All right, so thanks for, first of all, thanks for Seth for inviting me. Thanks for Maestro Bocelli for supporting this. It's a beautiful workshop. Let me tell you very briefly my story. I had some background in signal processing, in image processing, and computer vision. I used to work in the Jet Propulsion Laboratory, machine vision for robotics. When I started being a faculty member at UC Santa Cruz, I thought, well, we are teaching robots to navigate. Why don't we use similar algorithms to support blind people going around? That turned out to be a very bad starting point. The world is full of engineers like me that someday wake up and think, oh, wow, what I'm building, my hardware or software, is great, could be applied to solve the problems of blind people. And these efforts almost always represent big failures because they're technology-driven, because the user is usually considered towards the end. And I try that on my skin a lot. So the history of assistive technology for blindness has reported very few precious success stories. And I think we really need to learn from that. And that's what I'm trying to do now. I'm in a re-education phase where I'm really trying to understand how could I, at some point, someday, perhaps, maybe, build something that is useful. And to do that, I'm learning to take a critical look at each step that I take in a design of something. I am learning to run experiments with blind people. It's something that I've never been taught before. And I'm making a lot of friends who happen to be blind, and I'm trying to listen to them as much as I can. So as part of that, today I'm going to talk about how our effort in trying to build camera systems, by camera system I mean both a camera, which could be held in your hand in a smartphone, maybe supported as Google Glasses or attached to your lapel. How can we use a camera system to recognize things? And as James mentioned before, there are multiple things that could be useful. And the same thing as Seth has shown us beautiful examples, recognizing people, places, guidance to locations, reading text, taking pictures for fun. There are a number of blind photographers, recognizing objects in general. Now, one of the main problems, and James mentioned that, is that it is difficult to use a camera if you can't see through the viewfinder. Try to take a picture of something without looking through the viewfinder. It's likely that the picture is not going to be good. Maybe the object you're trying to take a picture of is not going to be even in the picture. I'm not the first one that noticed that, but part of this research that's a grant supported by the NIH is exactly trying to understand how a blind person can operate a camera without seeing through the viewfinder to detect and recognize a target, but also how can we design a system that not only looks at the technology, but also looks at the human factors that are involved in using a camera without sight. And I like this very simple slide because vision is an action itself, even for sighted people. We need to move our head, we need to go around, to get close to objects to see them better. If you are blind and you want to use a camera system, well, your vision is mediated by the camera and the interface. And it's really important to understand that these things, the camera, the hardware, the interface which mediates, and the action of the user who relies on the interface and their own perception are interconnected. We need to understand all three of them. And the camera system per se, I like to think of that in trying to simplify in multiple, again, interconnected components. The field of view of the camera, the resolution of the camera. If the resolution is low, I can see things far away, but what matters is really spatial resolution, which is a combination of the two. The computation, which could be done at the local level, could be done on the cloud, or maybe it is somebody else who looks at a picture remotely and tells you what the object is. With computation comes delays. So for some actions, I cannot afford long delays. For other actions, tell me what type of can is this in my hand. Maybe I can wait for 10, 20, 30 seconds. And the algorithms, of course, with all the problems the algorithms may have, they may be good or not. They may depend on the lighting and etc. Now, I have big faith in computer vision. And I think someday the algorithms will be taken care of. We're going to have perfect object recognition systems. So let me remove that. And in the experiments that we run, we cannot get away with that. I use what I call a gold standard of I don't know if it is a correct term to say semi-Wizard of Oz. I'll show you. We basically create a special system such that the recognition, at least that part, is completely taken care of so we can concentrate on all the other components. Now, I'll show you experiments that we run in using cameras to do two things. The first one is recognizing text, something, of course, very important. And there are mobile OCR systems that work actually pretty well, but as James reminded us, only if you can take a good picture of the document, which is difficult to do without sight. Now, there are mobile OCR systems especially designed for blind people. And I like to categorize the modality of these in two different families. One is a guidance. The old KNFB reader kind of was like that. It was a system by which we would take a picture with a Nokia cell phone, and then you try to hold your camera steady, and after a few seconds, many seconds, the system tells you, oh, I can only see 80% of the page, it's a little bit skewed to the left. So you're supposed then to rotate the phone, try again. It's kind of a trial and error with guidance. Other more modern systems like say Text Prismo or Text Detective, they operate on a different principle. They have a very fast text spotter, like the type that Seth mentioned before. They let you move the camera over the document you're looking at as soon as, so these pictures are taken, processed real fast with the text detector. As soon as the system thinks that there is a good picture, then the OCR, which is much slower, is invoked. So what we were trying to do in this set of experiments were to understand, all right, would the real-time guidance, not the old KNFB, make it really simple to take good pictures of documents? And how does it compare with this opportunistic shooting in which I just move the system, the camera over the document, at some point a good picture hopefully will be taken? And also want to see whether these could be used as training tools to help a blind person learn how to take a good snapshot of a document. So these are Wizard of Oz. We did away with the text completely. We ran experiments with some AR markers that are very useful because there is software out there, we didn't write it, such that if you take a picture of at least some of these markers, the pose, location and orientation of the phone is perfectly computed. After that, with knowing the optics of the phone, you can infer whether that picture will be a compliant picture. A compliant picture means that there's a picture that contains the whole document at high enough resolution. So we use this system here, and we ran a number of experiments with 12 blind participants in 3 phases. In the first phase, we asked them, okay, here's a document. Here's an iPhone. Try to take a good picture of the document that could be read by an OCR. And we'll tell you that the distance should be about 1 foot and 1.5 feet. So this is an example of that. She's moving it.
Snapshot taken.
She pressed the button and a snapshot taken with no other type of feedback. All right, so after this pre-intervention phase, we ran the system in either a guidance or an opportunistic shooting modality. So this is how the guidance, real-time guidance that we built would look like.
Up 26 and 4, what's 4?
Up 26 and 4.
Pose compliant.
So see some directions about where to move the phone next. Half the subject did that, half the subject did an opportunistic shooting where they were asked to just move the cell phone over the document until the system recognizes that a compliant picture will be taken.
Pose compliant.
Voila. This guy was really good at that. Normally, other people were not as fast as him. And then we had a post-intervention phase where people were asked again to take snapshots. So we'll see whether, thanks to the feedback, would they learn. So what have we learned by looking at that? What we see here is a graph across subjects of the success rate for snapshots before and after. So, you know, how many times you've been able to take a compliant snapshot before it's red, after it's blue. So what we learned is that some people are really, really bad, and some people are really good. The variance is huge. Some people are just, they have it, they know, they understand how to move the phone. They somehow understand the geometry of the sheet by touching it. Some people, even after, were not able to do it. Now, in general, in a post-intervention phase, through the feedback, a good number of people improved the technique. Well, maybe this is acceptable training, although not everybody did. Now, the most interesting part, and I would say the most troublesome, is that these are the times to success using either this guidance or opportunistic, will turn out to be more or less the same, meaning that it is not clear that giving these directions, this guidance, buys out much more than just letting a person move the phone until the system recognizes that a picture is taken. So we are still scratching our head on that. We think we have some justification. Maybe our guidance was not good. But see, we would have never found this if we hadn't run these experiments. Now, the second type of application we've been looking is guidance to allocation. So think of the example of Jim where somebody's trying to find, for example, your sugar box. Or think of other cases in which you might try to look for the door of an elevator at the restroom or the water fountain or something. Well, again, we want to find a gold standard with our system, and we created these color markers. So imagine instead of the sugar box, you have these particular color markers. We built them in such a way that recognition is really good. Okay? It's not realistic, but building these markers here, using them in indoor environment, you're guaranteed that with the software we have, you get an almost foolproof recognition. So we use this, and we started running a number of experiments a couple of years ago with 8 blind subjects, placing these markers around. These markers are different types, and we can program the phone each time to only recognize one marker, and asking them, okay, go find a marker and walk towards the marker and touch the marker. So here is a little bit of a collage of 3 different situations. You hear a lot of multiple beeping. This is the beeping of the phone that detects the marker. So in some cases, we experimented with marker attached to the wall. Some cases, they were in a big room. Other cases, in a corridor. This is somewhat similar to Jim's experiment with the sugar box.
Oh, here we are, right here.
There you go. So, with these preliminary experiments, we learned a bunch of things. First of all, it is not so easy to do this task here, so be guided by the camera. But especially, we realized there are 2 phases. The first phase is exploration. I have no idea what the marker is. I need to move around and search with my camera. And that takes some ability. You need to be aware of your position as you explore the environment. Once the cell phone starts beeping, you find a marker, and you want to get close to it, that's the guidance phase. It's a completely different set of skills. It requires good proprioception for you to hold your cell phone and walk in the direction of the cell phone, which sounds trivial, but it is not. And oftentimes what happens is that you lose lock with the marker. Maybe you're pointing in the wrong direction. And at that point, you have to start the search again very often. Remember, if you are blind, anything that is close to you, but beyond arm's reach, in this case, beyond the cell phone angle they're exploring, maybe 1 mile away. You don't know where it is. We had a situation with a person having a marker right there and exploring desperately nearby. It's a difficult task. So based on that, and then we ran an experiment with James and I. We explored just the guidance part, and we wanted to now study a little bit how different designs of the system, and in particular, remember these parameters, field of view, frame rate, how those would affect the ability of being guided to the marker. Because we thought, well, if there is a problem with losing lock with the marker because you're moving the camera, the marker exits your field of view, maybe I can just expand the field of view, make it very wide, so it never leaves, right? Also, we wanted to study the frame rate, because this system runs real fast, but not any computer vision will run that fast. So how slow can we go? So we tested with a full fast speed and also with a slow frame rate, about 1 frame every other second. We experimented with 18 blind participants in 2 sites with these 2 parameters changing, with the goal of taking a good picture means getting close enough to the marker so that you can take a good resolution picture head-on as you move closer to that. This is just one example of one of our participants doing that. The cell phone will beep just at 1 marker. This is with a slow frame rate.
Turn left.
And with a wide angle, you see a small attachment on the iPhone, which makes it a fisheye.
Turn up. You have reached
So you notice there was a feedback, a different feedback, where there was a spoken feedback that would help you orient the phone such that the marker would be head-on, and another simple feedback would beep if you are in view and beep faster if you're closer than 50 centimeters. This is a very primitive and simple feedback interface. We have experimented with more complex multiple tone interfaces, and we noticed that people tend to get really confused real soon. That's why we kept it really minimalistic, even though I'm not claiming it is optimal. Now, what did we expect? We were expecting that increasing the field of view, guidance would be better. We also expected that with lower frame rate, things will be much worse. In fact, I did not really think that guidance with such a low frame rate would be possible. What we found was something different. Wider field of view, almost always, is not good. And for most scenarios, we were able, I think, to find a justification for that. The justification is based on geometry, for the most part. It's based on the fact, basically, that if you increase the field of view for the same resolution, you have a lower angular resolution each pixel, which means you need to get closer to things to take picture with the same resolution. There is also another issue, that if you have a very wide field of view, you need better feedback, because you move the camera and your object is still within the field of view, but it might be really to the left and you have no idea. So certainly wider field of view calls for higher feedback. We also found out that, yes, lower frame rate definitely decreases the performance for narrow field of view, not so much for wide field of view. Actually didn't make much of a difference. And that's probably because if you receive instructions at a slow rate, but you're moving and the object is still within your field of view, because you can still move quite a bit the phone without losing lock with the object. So that's kind of good news. So we are not so bound to extremely high frame rate if you are using wide field of view. I just want to finish again with this slide, which I think is what we really need to concentrate. Again, being able to use a camera to do something useful requires an action. The action is mediated by the interface. The camera system must be designed in a way that takes interface and action into consideration. So we hope that we at least started a methodology to try to have a sound experimental way to investigate these issues. And let me end with a little product placement, if you don't mind. This is a book that my colleague Shri Kornewan and I recently edited, Assistive Technology for Blindness and Low Vision. We didn't write it. We had a lot of authors. And I would say we've been very lucky with the crop of authors that we had here. So if you're interested in the application of technology, multiple aspects of that, for blindness and low vision, buy a book, I'll buy you a coffee. All right, thank you.
Okay, now if you want to give some question, we can do it during lunch. And I want to remind you that during lunch there is the exhibition going on outside. So I'm inviting all of you to grab their food and go outside for the exhibition. And we will start again here at possibly at 10 minutes to 2.